Continuing on with our lecture on secondary metabolism, so let's look at the role of the secondary metabolites in the physiology of the organisms producing them. So we have several hypotheses to explain why organisms have why we have this secondary metabolism. So the first and the foremost hypothesis is the competition hypothesis. So under this hypothesis, it's actually an explanation why the secondary metabolism occurs in the idiophyte where there is a less amount of nutrients available in the culture because you have a lot of, basically it arises from having a lot of organisms that are vying for the limited resources. So under the competition hypothesis, according to this one, we have the secondary metabolism to ensure less competition by killing off the competition. And this is seen through antibiotics. Usually in co-cultures, in a culture where you have your antibiotic producing organisms in the wild, these are the fungi, because the antibiotics usually, or most of the known antibiotics come from the fungi. It's a way for the fungi to ensure that no bacteria will compete with them, win their resources. So you kill off your competition. So the next one is the maintenance hypothesis. So according to this one, secondary metabolism keeps cellular metabolism working in a working order when there is no growth. So when we say no growth, that means in a batch culture there is no cell division happening. So this is just to maintain normal life rather than the usual, because in the exponential phase, the life cycle is feed, grow, and then multiply. But again, during the stationary phase, there is no observed growth. So basically, secondary metabolism, basically your organism switches gears. And that is where secondary metabolism comes into play. That's according to this maintenance hypothesis. The next one is the unbalanced growth hypothesis. So under this hypothesis, it explains that it converts the products of primary metabolism to another product, preventing unbalanced growth. So again, this is started off because of the lack of resources. During the time when you have in the stationary phase, there is basically um, almost no available resources, almost no available food because all of the food have been eaten and exhausted. You have now the organism is now looking at new sources of food. And so, according to this hypothesis, the secondary metabolism kicks in because under secondary metabolism, the cell can recycle the products of the primary metabolism so that they can continue on living and growing. The other one is the detoxification hypothesis. So this hypothesis, according to this hypothesis, secondary metabolism converts toxic intermediates to less toxic products. This is seen in the production of penicillin, whereas one of the intermediates is penicillinic acid, which is very toxic even to the organism that produces it, and so it converts it to a less toxic product, which is benzyl penicillin. Now, another reason or another point of view where this hypothesis comes from is when, again, during at the end of the logarithmic growth phase, where you have a total lack of resources, nutrients, but you have a built up of the metabolic byproducts. Basically, these are the unwanted products of from the primary metabolism, and mostly these unwanted products are quite toxic to the cell. Case in point, in the production, in Saccharomyces cerevisiae, for instance, alcohol, ethanol, which is the byproduct of your alcohol, which is the byproduct of the fermentation of Saccharomyces cerevisiae, you have it can actually kill. So there is a limit to how much ethanol can Escherichia produce, because otherwise they will die. So that is why we have this detoxification hypothesis. It's a way for the organism to adapt because of the build up of the toxic byproducts. So they want to detoxify the toxic byproducts. So another hypothesis, the regulatory hypothesis. So under this one, secondary metabolite production is known to be associated with morphological differentiation in producing organisms, such as some substances that are only produced during sporulation. This is found in organisms which have where the life cycle is not very simple. So you have a budding life cycle and a sporulation life cycle. So it switches off from one life cycle to another, and that is again secondary metabolism. So the hypothesis of secondary metabolism as expression of evolutionary reaction. So this is under this one, secondary metabolic pathways is used as a fallback or an alternative pathway in times of need. Basically, it's already there, but it is not used. It's just an alternative in response, again, to external stimuli. So let's look at metabolic pathways on the formation of secondary metabolites. So the unifying feature of the synthesis of secondary metabolic products by microorganisms is that you have a conversion of a normal substrate into important intermediates of general metabolism. The assembly of these intermediates in an unusual way by means of a combination of a standard general mechanism with a selection from a relatively small number of special mechanisms. So basically, again, because secondary metabolic pathway is unique, so these are some general features that you can see in the secondary metabolic pathways. So one is that it stems from, or the starting point of the secondary metabolic pathway are the intermediates or even the products of the primary, or what you call the general metabolism. Another one is that they also recycle some pathways or some reactions from the normal or the primary metabolic pathways, but with slight changes or slight differences. Now, the special mechanisms, while being peculiar to secondary metabolism, are not unrelated to general or primary mechanism. So, for example, the addition of functional groups, for example, methyl group or an acetyl group to a certain intermediate. So, we can actually find them in general or the primary metabolic pathways, but the positioning, the modification, what particular molecule is being modified here, that's generally what is different. The synthetic activity of secondary metabolism appears in response to conditions favorable for cell multiplication. That's another feature. So again, the organism is adapting, and the secondary metabolism appears in the moment where adaptation is very apparent. And again, for most organisms, the drive for most organisms are to divide, or rather to multiply. So here is an example of a secondary metabolic pathway. So here is your glycolysis at the middle. So glycolysis is very common to your this is very common to most organisms. So this is glycolysis. You form from glucose, you form pyruvate. This is EMP. And then you have the Krebs cycle. So as you can see here, you have branches. So most secondary metabolic pathway starts off from the intermediates or even the starting point and end points of the primary metabolic pathway. So this is primary metabolic pathway in the middle, and branching off that at the sides is your secondary metabolic pathway. So from the starting point of the primary metabolites, you form the secondary metabolites. Antibiotics, kojic acid, ergo alkaloids, chloramphenicol, polyketides. You have steroids, carotenoids, aminoglycosides here, from branching off from this pathway. So, for the secondary metabolic pathway, so here are some usual or classifications of the secondary metabolic pathways. So, the secondary products derive from an intact glucose skeleton. So, the entire basic structure of the secondary product might be derived from glucose, like in streptomycin, or it may form the glycoside molecules to be combined with the non-sugar to form another biosynthetic route. So you can see here, this is a metabolic pathway that stems from a glucose skeleton. So this starts off from glucose or a derivative of glucose. So you have a sugar as a starting point. So here is an example. This pathway usually seen in actinomycetes. So you have here some antibiotics. Here is the biosynthetic pathway of streptomycin. So it started off from glucose, and you have streptidine. So this is the structure of streptomycin. So here you can see why we say that secondary metabolites produces unusual or bizarre structures, because this is actually not a common structure, or rather this is an uncommon structure. So this is your streptomycin, which is a commonly known antibiotic. So this derives from a glucose skeleton, and the vestiges of that source is still here. So you have similar to a glucose here. Although it's not strictly glucose, or rather sugar, it's not strictly a glycoside, but still you can see that it comes from a glycoside with slight changes. So here is the nucleosides. So these are secondary products that are related to glucosides. So we have the pentose phosphate pathway as the starting point. So you have many secondary metabolites in this group. These are usually antibiotics that are produced mainly by the actinomycetes and fungi. So not only glucose as the source, but also nucleosides. So example are the bleomycin antibiotic. So this is your bleomycin. So again, bizarre and unusual structure. Actually, it's a large structure, sa large amounts of functional groups and even rings in this structure. It's actually a large molecule. So another type of secondary metabolic pathway, this one is rather more well known. This is the shikimate chorismate pathway. Shikimate chorismate because some of the intermediates are shikimic acid and chorismic acid. So this is an important route for the formation of aromatic secondary products in the bacteria and actinomycetes. So example is the chloramphenicol and novomycin. So this is your shikimic chorismate pathway. So you have here shikimic acid and chorismic acid as some of its intermediate. Actually, the most of the branch points here is your chorismic acids. So you form here some important amino acids and even actinomycin, some antibiotics and other, even chloramphenicol here, you have folic acid. So other important pharmaceutical products. So another secondary metabolic pathway is your polyketide. So a characteristic of this pathway is they are from fungi, where most of the secondary metabolites are produced by another. So actually, you will usually see polyketide pathways in the fungi organisms, in the fungus. So they bear similarity to fatty acid synthesis, but because fungus do not have generally adipose tissues or fats, rather the production is similar to your fatty acid metabolism. But anyway, here is some products under the polyketide pathway. So most of them are actually they are almost all are pharmaceutical products. So this is anti-tuberculosis drug, this antibacterial, erythromycin antibiotic. So you have an anti-cancer drug, you have a chemopreventive drug, so anti-cholesterol, immunosuppressants. So these are all produced by a polyketide pathway. As you can see, they produce actually very long and complicated chains and rings. So this is your polyketide pathways. So this is the polyketide pathway. So it branches off from acetate. That's why it's called fatty acid synthesis, because the structures. They are very large structures and they build up in a similar way how fatty acids are built up. So you start off with acetate, you add and add and add the carbon groups from the acetate. So as the chain goes longer, as you can see here, they have characteristic long chains. Because they are built up in a similar way as how we usually synthesize fatty acids in the primary metabolic pathway. Okay, so this is another view of your polyketide pathway. So it usually involves acetyl-CoA because that's the usual building block in the even in the fatty acid pathway. And then you add and add and add. You elongate the chains. You add functional groups and other molecules. So here is your another view of your pathway for erythromycin. So as you can see, additive and additive. It's actually quite complicated. So, secondary metabolic pathways for terpenes and steroids, they are the second important biosynthetic route from acetate. That leading via mevalonic acid to the terpenes and steroids. So, this is a pathway that is for the production of terpenes and steroids. So, fungi and bacteria synthesize a large number of terpenes, steroids, carotenoids, and other products following your isoprene rule. The isoprene rule involves you have first synthesis of mevalonate. That's mevalonic acid. That's a starting point. It's an intermediate. It's an organic compound metabolite. So it starts off with mevalonic acid, and then from there, you continue on with the synthesis. So mevalonic acid is derived from acetate or leucine. So acetate, acetic acid, or leucine, which is your amino acid leucine. And then dehydration and the carboxylation to give isoprene from mevalonic acid, followed by a condensation to give isoprenes of various lengths. And then you have cyclization or ring formation, and again adding further modification. So you add functional groups to your sterol ring. So here is your isoprene, and this is your mevalonic acid. So this is the starting point. So you form isoprene from mevalonic acid, and then once you form the isoprene, you build up using the isoprene, and then you cyclize it to form your steroids. So, other compounds derived from amino acids under secondary metabolic pathways. So, amino acids are one of the usual starting points. So, amino acids are derived from various products in the catabolism of glucose. So, they're also related to the shikimic pathway. So, here, example is your gliotoxin here, which is a mycotoxin, and malfornin from the L and D, leucine and cysteine. So these are compounds derived from amino acids. So as you can see here, you have a rather complicated ring structures here. So you have basically compounded rings. So important for secondary metabolism, regulation is very important, and that will be the subject of the next part of this video.